Good morning, all of you. We are in the seventh part of image processing. This is the seventh lecture on that. In the last class, we have discussed about how convolution and correlation can help us in performing some kinds of filtering on the image. In particular, we discussed about the smoothing filter, or you could think of it as in some sense as a denoising filter if there is some noise that got added to an image, or you may call it as smoothing, denoising, or if you want you may call it as enhancement also, if that happens to be an enhancement to your image. And in that we have discussed about average filter and weighted average filter, and we have in fact derived expressions on how this can be written as an operation, as a 2D correlation operation. This is what we have. This was the resultant expression that we have arrived at. For example, the multiplications with the weights with which you want to multiply your neighbors are encoded in your kernel H, and your I is your image. And what turned out to be is that this operation is in fact equivalent to a correlation operation. That's what we arrived at. We did not just stop there. There is an equivalent other very well familiar operation, particularly for those of you from the signal processing background, is convolution operation, right? And then we have seen how a convolution can be looked at as a correlation, and a correlation can be done using convolution. What is it that you have to do? Suppose I give you a function that perform convolution of a given image, okay, your image I, with a given kernel H. So what I have given you is a function that takes I comma H, performs the convolution and gives you the output. But I want correlation. So how do you do that then? Using the same function. So
Multiply and
you give as a kernel, H1 will be now what you give as an input to H1 is a flipped version of H, is what you give it. Same duality holds good for correlation also. If I give you a correlation function, you want to do convolution, you simply flip the image in both x and y, right? X and y, that means typically the center will be the origin for you, and that should give you that. Okay, so I will conclude this and move to the new chapter by asking you one more question. When will be correlation operation and convolution operation will give you the same result? When will both correlation and convolution with a given filter H would give you the same result?
when H is symmetric,
Correct. Symmetric with respect to what?
both
Any,
X and Y axis, like
right. So basically if your H I comma J is also equal to H minus I comma minus J, if you want me to put that mathematically. Now you see the expression here for convolution. I could then minus I comma minus J, I could put it as H I comma J. If I put H I comma J, this operation is same as convolution and correlation are turned out to be the same result. This is a very important thing. And one more important point I want you to make a note here is most of the filtering operations will be typically, there are quite a few, if not all, where you have symmetric mask. For example, both the masks that we have seen earlier, so this was the mask that we considered for doing a weighted averaging filter. Is that symmetric or not?
yes, sir.
Yes, you could see here, you flip the rows first. So 1 to 1 and 1 to 1 gets exchanged, means they would remain same. Now you do the flipping vertically. Again here 1 to 1 and 1 to 1, right? It's in fact a 90-degree symmetry is also there, not just that symmetry, which is good. So not just this mask, you would realize in many things, there are quite a few operations or filtering operations where you would arrive at a symmetric mask. And that's a good thing. You don't really have to distinguish between correlation and convolution anymore when your mask is symmetric. Is this point clear to everyone? Right. Well, for smoothing and denoising or enhancing, we have empirically set the weights when it came to weighted average filter. But in fact, you could in fact use a Gaussian filter also to fit those weights. How do you do that? For example, Gaussian filter. Okay. I should have drawn this line somewhere here. Okay. A Gaussian filter continuous version I am taking. The moment, well, again, this is a 1D Gaussian I'm right now drawing. For an image, I should have been drawing a 2D Gaussian. I'll show you the images rather than entertaining you with my drawing skills of a 2D Gaussian. Okay, let's, for an example here, I'll take you with a 1D Gaussian there. What you will do there is, for example, this whole average or something that represents an equivalent of this range, you would take one value, let's say this value, because, well, or yeah, so for some reason you could take that this might represent for some region. Okay, so then you might take some other value here. Then similarly, there is high and low till here, you might represent this value. And similarly, you could discretize the values there. And your kernel could be a kernel where this value would become the center value here, then the value could come here, the value could come here. Same is this thing here. Again, you could notice here, as it is centered there, this will be a symmetric mask. So convolution and correlation would be the same thing there. So let me show you. So let's call me as G of, let's write an expression for 1D first. Let's call your variable as X or parameter as X, or yeah, variable. And one you need to fix for a Gaussian is sigma. I give you a particular value of sigma with which what variance you want. That could be a curve like this, as you all know, right? I don't have to draw further. Or it could be something like this with a large variance. Correct. Can you tell me the expression for Gaussian, 1D Gaussian?
Root of 2 pi sigma
Root 2 pi. Is sigma inside the root or outside the root?
outside
Right. Sigma into
e power
exponential of
minus
uh,
x square by
2 sigma square.
just sigma square.
right. Right. That's the expression. Of course, we are taking a Gaussian centered at origin because this is the filter. You take it, and with this center, you keep it at each pixel. So I don't have to consider a mean value there. And it's a different weighting that you are in fact giving. It's one kind of weighted average filter only. It's a special case of weighted average filter. You could see at the center there is very large weight is there. As you move away here in this direction, the weights are reducing, and after beyond a particular point, the weights are becoming negligible. Correct. And of course, which Gaussian, how do you want to vary these weights? It could have been something like very bad drawing of a Gaussian, but I'm sure you are wise enough to know what it should have been. Okay, so by varying sigma, you could change the rate of at what rate you would vary it as you move away from the center. Another important thing here is, while you discretize your, a discretized expression of Gaussian is what you are finally using, right? Suppose this is your center pixel, okay, at a 0. So you need to also fix, what is it that you need to fix in addition to sigma? How do you call this? This is referred to as, I know, I understand what you mean, that the window size of your kernel. Okay, that's the proper terminology. I'm sure you, I guess you mean the same thing, right? It's the window size of your Gaussian that needs to be fixed. So a typical, the rule of thumb for doing this is you have 2 times sigma plus 1. If you don't mention anything, by default, most of the tools will take 2 times 2 of sigma, if I am not wrong. 2 times, right? 2 times 2 sigma. And of course, this they take it as seal value, 2 star seal value plus 1. What does that mean? I have, for example, sigma equal to 4. Okay. That means for your Gaussian function, of course, 1 will be there at center. That is there. That is what this 1 is coming from. On this side, now, of course, if it is 4.1, you would have taken 5 on each side, but let's, for the time being, consider simplicity. For simplicity, consider 4. So that means this whole thing you would divide into 4 parts here. So you have 1, 2, 3, 4 on the side, 1, 2, 3, 4 on this side with the equal distance. And then you take that area under the curve and then average it over that particular region. There is a way you could just figure out what would be the average value over that region. You would do it. Is it making sense on why we should increase the window size with increasing value of sigma? What could be the rationale for it?
Because the variance is increasing.
Correct. Exactly. So how can you interpret in terms of image the same statement? The value that you are going to assign here would depend on the pixels that are far away also when your variance is high. Okay. So with that, you are doing a Gaussian smoothing. That means you look for more neighbors essentially. So that means, hey, since you have a discretized version here, that means you are making it more. This is the least thing you would take, or by the default thing you will take. If your value is 4 center for this side, for that side, that means you will take a window size of 9 there. Okay. And of course, you could play with that also. Nothing wrong, even if you take more, but value wise, if you calculate, there won't be much difference there. So this you keep it in mind. There is not only sigma, although you won't be all the time setting this value of, but in the name and value, you could always mention there will be something to say your window size. Okay, that you could also set there. Clear? Or any questions so far before I go ahead?
Sir, this value of sigma will decide how many windows we are having, right?
Be more specific in your statement.
Sir,
Yes.
the number of steps that number of steps or the number of filters which we'll have either side of origin will
The
depend on the
window
value of
size. Yeah, correct. Exactly.
depend on this value of sigma, right?
Correct.
So
So
my question
windows.
is, if sigma is as we increase the value of sigma, then we are losing the edge information more and more, and the image is becoming more smooth. And if the value of sigma is less, then the edge information is being retained and smoothing is less. Am I right, sir?
That's absolutely right. So that's why you would, what is the purpose? Is it the edges or something else you are looking for in an image? What is the extent of uniformity that you would expect in your image is another thing. Definitely, if you are looking for some sharp edges, of course you will lose. There is always a trade-off between retaining edges versus smoothing. If you're doing smoothing means obviously the edge will get blurred. So what is your purpose? Is there some good amount of noise that got added to it? You want to get rid of that noise and then figure out edges. What exactly you want to do? And there is a trade-off there on the value you choose for sigma. As you rightly mentioned, more the value of sigma, the more blurred the image. If you have the maximum value of sigma, what will you get in your image? Eventually, if you keep repeatedly applying that sigma value, then you will eventually get, means I apply that Gaussian, I get something, again I apply, then I get something, then I will again apply. Finally, what is it that you would guess? what would be the image that I would get at the end of this iterative application of Gaussian smoothing? Can anybody make a guess? That means I have an image, I apply a Gaussian filter, I got some image, again I apply, and I go on in like infinite number of times. That means many large number of times. What is it my final image will be?
Single color, sir, as in there'll be no edges. It will be completely smooth.
Right. Very good. Very good. A single intensity is what you would be. Color, let us use the words to the extent possible very precisely also. If it is a grayscale image, there is nothing like a color. So there is an intensity, a single intensity. I understand you are saying the same thing, but let us try to be as precise as possible with the terms also to the extent possible. Correct. Can you make a guess on what would be that intensity? Since anyway we came so far on this point, so can you make any another guess on what could be very likely that intensity will be? Okay, you think about it then. Okay, yeah, I'll leave you there with that. Now, anyways, this is an example which shows you in uniform uniform weights, and the same sequence you apply these weights similar to what we worked out in the last class. And now you have, for example, when it comes to 2D Gaussian is what you need to use for smoothing a 2D image. And here, assuming that the 2D Gaussian in both X and Y directions has same variance, okay, then you would get an expression similar to this is the expression that you typically use, 1 by 2 pi sigma square into exponential of minus of x square plus y square by sigma square. You could use any variable there. They were using here just to avoid any confusion. They're using xy here. This as uv, this is u, this is basically u and v. This could be, then this could be the x and this could be the y here. And you go to each pixel, keep it there. Then when you, at the end of your all your exercise, you typically also will be writing it to the nearest integer. Okay, and because of that you ended up weights very similar, not very far from what you have thought earlier. So 4 2, so there is a maximum weight to that pixel, less weight as you move on, as you could see from the center in whichever direct. This is symmetric if you see it in all directions. So that's why this is 4 2 2. Now you went far, both x and y are there here, either u or v is there initially, now both are there. That has given you here 1 1 1 1. Okay, 1 2, so you got 1 2 1 2 4 2 1 2 1. This is your center. That's what you got there. That symmetry you could also see from a Gaussian. Of course, since the continuous version of that continuous Gaussian has it, the discretized version also will have that symmetry. Now you convolve. Should I say convolve or correlate or anything here? Right. Either of them or any of them you could mention there because it's a symmetric mask, right? Any, so this is how, for example, you take a variance of 2. Sorry, yeah, this I should call it as a standard deviation of 2, I should call it, right? And of course, just one thing, I make a correction to what I told there. The sigma is a standard deviation here, not the variance. That was a mistake from my end. Please correct that. That's the standard deviation. So typically what we said is 2 times 2 plus 1. Typically this 5 is usually good enough because that will anyway die down fast, right? Because after 2, 2 times sigma, how much will be there? Some 67%. I don't remember exactly. We'll anyway come to that in the subsequent classes and all. So it will decay fastly. So here with the same logic, I should have 2 into 5 plus 1. That should be 11. Now a discretized version of the kernel is shown here, as you could see. Now these are the kernels which has a size of 30 by 30 here. Same 30 by 30 is used here. And of course, with a larger variance, you see the values being non-zero here. The blue is indicating 0. You could observe that the color coding from this mesh plot of your continuous time Gaussian. Of course, you cannot plot continuous time Gaussian. It's just that for more decimal values are also in between also. Maybe from 0 to 1, you made 100 divisions and plotting it. So don't mistake that you are able to manage to plot a continuous Gaussian in your MATLAB. That can never be done. Okay, that's why you would even see almost the same color coding there. That means you are in fact a constant color means that's the kind of the finer division that you have made there. Anyways, coming back. So you could see here when your standard deviation is small, larger beyond this part, all is 0. Okay, of course, this is symmetric both in X and Y flipped versions as well. On the other hand, this region has reduced. So that's why typically when it has a very, very small value, then multiplying and adding, and finally what you are doing, this mask, you would multiply and add when these other, suppose if I further consider here bigger bigger square and take them when these are very small, when I add up the difference, that would become with very decimal values there, the small values compared to the other ones which are there at center. The variation in your intensity that you would be getting will be very minimal. Change in variation will be very minimal. So that's why that tells you some rough empirical value that you might use there for Gaussian filtering. That's what I wanted to, again, we would Gaussian is something, or the Gaussian distribution to be more precise, is something that we will again come back and discuss in a lot more detail, step by step, when it comes to the machine learning part. In more specifically, the Bayesian learning part, when we come, we will discuss it in more detail, right? So question is, in the filter size slide, it is given filter size is 2 times 2 sigma. So for a sigma equal to 5, that's correct. If sigma is 5, you have a size of 21. That's correct, right? Yeah. Abhay was asking that, so you are right. When do you think, what should be the properties that should be satisfied such that I can do either I can transform a given kind of filtering into performing a convolution or correlation? They can be, now let us may use it interchangeably unless the mask is not symmetric. So what are the scenarios under which you could transform a given filtering operation into a convolution operation?
Linear functions.
Is the linearity good enough? Linearity is of course required. Is it sufficient, or something else is also required? Or I'll tell you answer, give me the justification for it. I will also write shift invariance here. Why do you think shift invariance also is required? Can you just think loud and give me justification? I gave you answer, at least give me justification. See, suppose if my filtering operation or my kernel is going to vary at different parts of my image, at different parts of my image, then convolution essentially is, I'm sure you all have a very good background in signals and systems and DSP. From that, convolution operation, when can you perform on an image, is it should be LTI systems, linear time invariant systems. There, instead of time is 1D signal essentially. So instead of that, I'm now saying shift invariant here, because it could be in both X and Y. It's a multi-dimensional one. So I'm all saying is shift invariance. You cannot represent. So in order to write something as Y of n equal to X of n convolved with H of n, your system has to be an LTI, isn't it? So assume that for some reason, the way you do filter depends on which location it is there, or the content at that particular location. Then you won't be able to perform it using a kernel or using convolution or correlation. For example, if I want to fabricate one such situation, is that I know in particular region there is noise is varying in that given image. Okay, this is what I could fabricate. don't ask me for for what reason, then I have to fabricate further and why, or come up with some scenarios. But good enough for now is that your noise is varying over an image. So that's a shift. You cannot apply the same filter everywhere. So shift invariance has to be there. Or you could think of also that this, you would look at the gradients of the image before you apply a smoothing. And if when you see a large gradient, maybe for the reasons that we discussed in the earlier part of our class, that Gaussian also has, on one hand, while removing the noise, it will blur the edges. But somehow I figured out where the edges are there I want to deal with them differently. Then you cannot go simply with just one kernel and apply everywhere. Okay.
Regarding that Gaussian smoothing multiple times, will
Hmm.
there be like only white image at the last?
I won't say white. Consider an image where everything is 10, for example. I have 10 value everywhere. What may Gaussian do then? Think about it. I am applying over a centered pixel now. So when I add everything, what would I get here? I'll get 10. Correct. So that's like 4. If you remember, I have 4, 2, 2, 2, 2, 1, 1, 1, 1. So 4 into 10 plus 2, of course, then I'll finally have a multiplication factor of 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10, 10 plus 2, 12, 12 plus 4, 16. Okay. What will I get? Once I apply, I have a constant image. For example, I apply this Gaussian filter. What would be my output?
Same intensity level, like every
Correct.
pixel
So
of
it
same.
doesn't become, when you say white, it means, if you are assuming you are using an 8-bit unsigned character for storing them, it is 255, but you will not get white there. You will get 10 only. Had every pixel been 0, you would get 0 only everywhere. Correct. So it's not about white and black. It is about a constant intensity. If this is
Okay,
clear
sir.
to you, then iteratively you can realize that roughly it would be equal to the average, or rough, not rough. But if you are applying infinite number of times, you get whatever is the average intensity, that's where you will be ending up. Whatever the average intensity of this whole image, that's where you will end up. Is that clear?
Yes, sir.
Good. Any other questions?
Sir, why do we need to blur the edges?
No, it's not that we want to blur the edges. It is that, assume that some noise got added to your image. Assume that it's having a lot of spikes in it, or when you move from there to to frequency domain, you end up with high frequencies which you don't want. Or it could also be when you are looking at histograms and all, you expect some kind of, see, you look at this image, except around the edges. See, when my face versus background, my face versus this chair, within my face also, maybe my eyebrows versus my forehead, that is where you expect a change. But here you will not expect any sudden jumps kinds of things in practice, is it not, in many of the scenarios? So for example, for some reason, be it my camera has a problem, be it my bandwidth is low, and it has downsampled it to such an extent that it has resulted in some artifacts. Or be it your bandwidth is down on your end and you are looking at it, so you want to get a better image. What do you want to do then? You want to smooth the image. It's not to blur the image, it is to, I am telling what is not the answer, you tell me what is the answer. The purpose of Gaussian filtering is in general not to blur the image. That's in fact many a time an undesired effect, but to dash, fill in the blanks.
Remove high frequency noise.
Yes, but to get rid of the noise. High frequency noise also, I agree with that statement, because how can you justify me? Okay, since I'm tempted to ask these questions, although I wanted to finish quite a few things, but since this discussion has come, how can you justify that a Gaussian filter would remove high frequency noise?
Essentially, it is being used to remove noise, and generally, noise has high frequency.
No, noise can be in low frequency also. Why you are saying the statement what you made was earlier that Gaussian filter helps you to remove high frequency noise is absolutely right. My question now is, how can you justify that a Gaussian filter would remove high frequency noise?
Okay, sir. Like if we could take the the frequency response of this,
Hmm.
it would act as a low pass filter, thus
Very good.
removing all the
A
high frequencies.
Gaussian, the Fourier transform of a Gaussian is again another Gaussian, but with a change in variance. All that varies is its variance, but still it is a Gaussian. You could notice that with Gaussian, at the center you have maximum value, and of course, as it increases, its value would reduce. So when you plot here for the omega, you could see here a convolution is what you are performing here. So now it's equivalent to what there in the frequency domain? A multiplication there. For an image, you will take a Fourier transform that will give you the frequencies there. And now you are multiplying it there. Obviously, it is making all the high frequency content of your image to take the DFT of your image or DTFT of your image for the time being. You multiply it, you will see that all high frequency content has been made zero. That's the answer I was expecting. Hope it is clear. That's a good answer. Right. You are right. Is it clear to everyone? So next one we would take a look into is there is another type of filters, statistical filters also you could use. For example, does anyone know what is the kind of noise that got added to this image? What is it referred to as?
Salt and pepper noise.
Right. This is called as a salt and pepper. Why is it called as salt and pepper?
So salt and
Because
pepper noise have only two intensity values. Salt
very
refers
good,
to
right.
2255
Pepper
and
is
pepper
black.
refers to 0.
Yeah, if I may say pepper, I could consider it as black. Salt, I could consider as white. As you could see in this image, if there are here and there some high intensity values and some low intensity values are added, it could be called salt and pepper noise. Of course, there could be instances where only salt got added and there is only otherwise pepper got added. It is quite possible. So now you have seen already that suppose because of getting added of the salt got added to an image. Okay, ideally you were expecting perhaps a profile like this in your image when you take one row of your image, but because of the so you are discretizing it some points like this. Okay, that's the discretized values of it. Now pepper got added, so you got something like this. What well, this, let me, you consider this here. Okay, ideally it would have been here, but because of salt it moved there, that got added there. What will happen if I do a mean filtering? Notice that mean filtering, what will I do? For example, take a very small thing, 1 by 3 window here. I'm just showing you in 1D. You could instead consider 3 by 3 also, but this is easy to draw here and calculate also. How do I do for 1 by 3? Just ignore the first pixel because I don't have on the other side. Assume that in the output image in this particular row here, what I should replace with. How I do? I take a 3 by 3 window here. I sum them all three. Consider a simple averaging filter. Okay, add them all the three, divide it 1 by 3. Suppose next this pixel I want to do, then what I will do? I will do this averaging by centering my this window. I'll center this around each pixel and do it. Now, if I am using a mean filter, this is what I would be. Ideally, it is like this. But now, whereas that which is there here, this pixel contributed to this pixel, and this pixel, it has spoiled 3. Assume that I am using 1 by 5. It is spoiling 5 pixels intensity values. because one pixel went wrong. Is there anything better to do? Particularly when you know that the nature of noise that you have is salt and pepper. By that, what we mean, earlier version is there is a Gaussian noise that got added. So it's everywhere it's got added. This noise has a particular mean and variance, then Gaussian is good. It's not only you got corrupted, the sidewise people also got corrupted to an extent. So then it is fine. But now you know there is an application and an instance where you have this prior knowledge, or you learned, for example, if not prior knowledge, through something, that the kind of noise that got added is salt and pepper. Again, it's not just about this getting affected. Also make a note to the rest of the region. Ideally, you have a kind of sharp edge here, right? And then there is this edge, which is a ramp is there. But the moment you are applying this Gaussian filter, you could notice here, because for this pixel, what you do, this pixel value equal to average of this plus this plus this, right? You take some, and obviously what would happen then? Well, these are same values, one of them is high, so it will move somewhere here. So finally you will get a curve like this, as you could see here. And you could see here where there is a sharp edge, those sharp edges got spoiled. It's not only the whole profile, but even the edges got, where actually there was no noise that got added, also got spoiled. So there could be such instances where other filtering things also you should make a look into. Statistical filters, for example, a median filter. Median filter, how you do it? I think I have spoiled this slide too much. So let me just erase them now and come back here. Right. A median filter, how do you do that now? For example, ignore the boundary pixel. This is the pixel I want to find out. So how do you find out the median value over a 3 by 3 region? Or here 1 by 3, because that's 3 by 1, which are you consider. So how do you do that now? Median value for that pixel.
Like increasing order and then take the middle pixel.
Right. So should it be increasing only? Can it not be decreasing?
It works for both.
Correct. It works for both, because you are anyway taking the middle value. Correct. Either you are in, of course, here you are taking an odd number of pixels here. Okay. One, and then say this side some m, this side m. Okay. So that is 2m, and myself 2m plus 1. 2m plus 1 is always, of course, 2m is an even, 2m plus 1 is odd. So a median would remain same whether I go for an ascending order or descending order. So you take here for this pixel, all are having same value, it would remain same. Come here now, I would consider this region now. What is going to happen? All are same, it would remain same. Now come here, what is going to happen? For this, I would consider this range. Now again, these all are same, so it would remain same. Now look at this. This window is, these three values are there. You put them either in the ascending order and descending order, then you will see, suppose let me write it as 10 and this as 20. So what you have is 10, 20, 10. You put them in ascending or descending order, 10, 10, 20. Take the middle value, and that is what you assign to that particular pixel of your interest, which is currently this. So you will see there, you will get 10 itself here. Same thing here happens. So when this pixel is there, what are the values there? One before that is 10, that pixel is 10. Below this, let's call this as 0, for instance, 0. You put them now, let's keep them in, let's say, is that correct? For this pixel I'm considering here, or which is the pixel I was considering? Okay, for that I considered this, in fact. So that's why 10, 10, 0. So then this is descending order, doesn't really matter. So I take 10. You consider this pixel now. What is that here now? I have 10, I have 0, I have 0. This is again descending. I could have done ascending. Middle would remain 0. So notice this thing. it is removing the noise while also retaining the edge information much better than a simple mean filter. If there are no questions, I have a question for you. Now tell me, what is the filter? Now I want to perform the same thing as a filtering operation. What should be the filter I should use to perform this median filtering, so that I could then do it either with convolution or correlation? So think about it. If you can't immediately answer, think about it and answer me in the next class. So this is just salt and pepper, heavily added salt and pepper noise here. You could see, of course, there are peppers also along with your salt and pepper noise there. And you get a very good image here. And if you draw just one row, this is how it is. You could see how nicely these edges are retained. Again, don't fall under the conclusion that median filter is better than Gaussian filter. Is median filtering is indeed better than Gaussian filter, not universally, but when is it better? Under what condition?
When we want to preserve the edges.
That is one reason. I agree with you. Median filter preserves edges under all conditions compared to the other one. That is, I agree. But this is a median filtering is better than Gaussian filtering when?
The noise is impulsive.
That's all. And the type of noise that got added to your image is of salt and pepper in nature. Even if it is just salt or pepper or both, in all these conditions, it is better. Okay, then I'll stop here. Bye. See you in the next class.